When you think of mammals, you probably picture animals that walk, run, or swim. Lions, whales, maybe your own dog. But one group of mammals broke the mold: bats, the only mammals capable of true, powered flight. Unlike flying squirrels that merely glide, bats flap their wings and soar, owning the night sky. Bats belong to Chiroptera, meaning hand wing. Their wings are skin stretched over elongated finger bones, not feathers. This design gives them incredible agility in the air. With over 1,400,000,000 species, bats make up more than 20% of all mammals, second only to rodents. They live everywhere except Antarctica, thriving in rainforests, deserts, and cities. Their diets are just as varied. Some hunt insects, others sip nectar or eat fruit, and a few even hunt small animals or drink blood. This diversity shows how successful bats have been for millions of years. Bats have been around for over 50 million years, sharing the world with early horses and whales. For all that time, they've been perfecting their skills as masters of the night. Their story is one of incredible adaptation, a small mammal taking to the air and conquering a new world. Understanding their evolution unlocks a secret chapter in the history of life on Earth. Every story has a beginning, but bats' origins are a mystery. The oldest complete bat fossils already look like modern bats, fully formed wings, bodies built for flight. We're missing the proto-bat, the crucial fossil showing the transition from climbing mammal to flyer. Why? Bat bones are thin and fragile, great for flight, terrible for fossilization. Only in rare places, like calm lake bottoms or caves, could their bones be preserved. This leaves a huge gap in the fossil record. Scientists know there must have been small evolutionary steps from ground dweller to flyer, but the evidence is elusive. Finding a fossil of a bat ancestor that couldn't quite fly would be a game changer. Still, researchers keep searching ancient rocks worldwide, hoping for that breakthrough. The oldest confirmed bat fossils, just teeth and bone fragments, are about 56 million years old, found from Portugal to China. By then, bats had already spread across the globe. The full story of their origin is still buried, waiting to be discovered. Without fossils of the first bat ancestors, scientists rely on educated guesses. The leading idea is the trees-down hypothesis. Flight began in the treetops. Early bat ancestors were likely small, insect-eating climbers, leaping between branches. Over time, traits like larger hands or skin flaps helped them glide, turning risky jumps into controlled descents. This is seen in animals like flying squirrels today. Gradually, gliding evolved into powered flight. Skin flaps grew, finger bones lengthened, and chest muscles strengthened. Skin flaps grew, finger bones lengthened, and chest muscles strengthened. Eventually, these proto-bats could flap their wings, not just glide. Each small change, longer fingers, more skin, stronger muscles, brought them closer to true flight. Longer fingers, more skin, stronger muscles, brought them closer to true flight. The trees-down hypothesis shows flight evolved step by step, not in a single leap. It's a story of gradual adaptation, leading mammals into the night sky. In the 1960s, a nearly complete bat fossil was found in Wyoming's Green River Formation, Icheronecteris, from 52 million years ago. Icheronecteris had fully developed wings and could fly, but also had claws on its fingers, evidence of its climbing ancestry. Its skull showed it could echolocate, using sound to see in the dark. Then in 2008, scientists discovered Onychonecteris, an even more primitive bat from the same site. Onychonecteris had claws on all 5 fingers and shorter, broader wings, suggesting it mixed gliding and flapping. The big surprise: its inner ear bones were small, meaning it couldn't echolocate. Onychonecteris proved bats learned to fly before they developed echolocation. These fossils finally answered a long-standing debate. Flight came first, then sonar. Early bats were climbers and flyers, gradually adding new abilities. Each discovery brings us closer to understanding how bats conquered the night. Echolocation is one of nature's greatest superpowers. Bats use it to hunt and navigate in total darkness. They emit high-frequency calls, then listen for echoes bouncing off objects, building a sound map of their world. This lets them fly at high speed and catch tiny insects mid-air. For years, scientists wondered, did bats evolve echolocation before or after flight? The discovery of Onychonectaris, a bat that could fly but not echolocate, solved the mystery. Early bats likely hunted using sight and hearing, flying by day or twilight. Once flight opened up the night sky, the pressure was on to develop a new sense. Over millions of years, some bats evolved echolocation, becoming the ultimate nighttime predators. Fossils like Acaronectaris show echolocation evolved soon after bats took to the air. Flight came first, then bats became masters of the dark. For decades, scientists divided bats into two groups: Megachiroptera, megabats, and Microchiroptera, microbats. Megabats, like flying foxes, are large, fruit-eating, and rely on sight and smell, not echolocation. Microbats are smaller, insect-eating, and use laryngeal echolocation. This neat division shaped our understanding of bat evolution for years, but new genetic research upended everything. DNA analysis revealed two new groups: Yimpterochiroptera, including megabats and some microbats, and Yangochiroptera, the rest of the microbats. Some microbats are more closely related to megabats than to other microbats. The old classification was wrong. The real story is far more complex. This genetic revolution showed that bat evolution isn't a simple split, but a tangled family tree. It also raised new questions about how and when echolocation evolved. Science is always changing as new evidence comes to light. The more we learn, the more fascinating the story becomes. Bat evolution is a tale of surprises and constant discovery. The new genetic family tree created a puzzle. How did echolocation evolve? One idea: laryngeal echolocation evolved twice, independently, in different bat groups, a case of convergent evolution. Another: the common ancestor of all bats could echolocate, but some lineages, like fruit bats, lost this ability. Recent fossil finds support the lost superpower idea. A 50-million-year-old bat from France, Viritia cris, had the inner ear structures for advanced echolocation and sits near the base of the bat family tree. This suggests the ancestor of all modern bats could echolocate. Fruit bats aren't primitive, they're specialists who traded sonar for keen eyesight and smell. Evolution isn't just about gaining abilities, sometimes it's about losing them when they're no longer needed. The story of bat echolocation is one of adaptation, loss, and innovation. The Eocene epoch, 56 to 34 million years ago, was a golden age for bats. Warm, lush forests covered the globe, perfect for bat evolution. Fossil sites like Wyoming's Green River Formation and Germany's Messel Pit reveal a world buzzing with bat diversity. Messel fossils are so well preserved, they show fur, wing membranes, and even stomach contents. By 47 million years ago, there were already many bat species, each with unique diets and behaviors. Some fossils show bats feasting on insects. Others reveal their fur color, reddish-brown for camouflage. Fossils also show bats living in colonies, a behavior still common today. The rapid spread and diversification of bats during the Eocene proved how successful their new lifestyle was. By conquering the night sky, bats found a world full of opportunity and little competition. This explosive evolution set the stage for the incredible diversity of bats we see today. The story of bat evolution is more than a scientific curiosity. It's a lesson in adaptation and innovation. Bats show how gradual changes can lead to extraordinary new abilities, like flight and echolocation. Their history is a detective story, with gaps filled by fossils and genetics, and old ideas replaced by new discoveries. Understanding bat evolution helps us protect these unique animals today, guiding conservation efforts. Their past reveals how they survived climate change and adapted to new challenges. Bats' journey inspires wonder, connecting us to a deeper history of life on Earth. Behind every fleeting shadow at dusk is a 50-million-year saga of survival and success. By unveiling the secrets of bats, we learn about the resilience and creativity of all life on our planet.